Today we'll talk about why our benchmarks, the favorite ones, TPC is just not enough for our customers. I will talk about the insights from this paper we published at VLDB 2024, why TPC is not enough, and the accompanying data set to it called RedSet. RedSet contains query patterns, workload patterns, data patterns from Amazon Redshift customers. So put all this then in context, I will go back a little bit and talk about evolution of business analytics use cases over time. I will motivate that a new breed of use cases are coming up which challenge databases of today. And these use cases are not adequately represented by TPC benchmarks. I'll present a case study derived from RedSet and show that query patterns and the data patterns we have observed in the RedSet do provide this insight. So let's go a little bit back. Back in 1980s, the only way for a business analyst to come up with business insights was to walk up to a DBA, explain the business problem to them. The DBA would write a SQL query, submit to the database, publish reports on paper, like charts and tables. In 1990s, this began to change. Business analysts got access to personal computers in office. And first, business intelligence software started to show up, like Cognos reports, business objects. For the first time, business analysts could drag and drop tables and columns on their PC, and the SQLs would get generated. They would run these SQLs against the database, and the charts and tables would show up on the screen. And they would do it iteratively. DBAs in this era became like data engineers of today. They would curate and create these data sets for business analysts. To capture this workflow, TPC created the first benchmark for decision support systems, TPC-D, back in 1994. It was a very simple star schema model. It had 17 ad hoc queries on the tables and 2 refresh functions to update the table. This was, 1990s was an era of big data. The data was increasing fast. So the refresh, from the first refresh of this benchmark was TPC-H, which was released in 1999. Here, the data set increased from 3 terabyte in TPC-D to up to 200 terabyte for TPC-H. The number of ad hoc queries increased to 23, and they became a lot more complex. In 2000s, the complexity of data modeling kept increasing as business intelligence went on to newer and newer departments, newer and newer industries. In the next refresh in 2012, called TPC-DS, TPC created a much more complex data model based on Snowflake schema. And it had multiple sources of data which the queries can draw from. The number of ad hoc queries was increased to 99. The queries became even more complex. But overall, the flow of information remained the same until in late 2010s, when business intelligence software started to get delivered online. At this time, the business intelligence software started reaching what we call line of business users, like support, sales, operations. Some businesses even put the analytics on user data within their customer-facing websites. For example, I wanted to cancel my Amex card. I called the support, and the support person told me I had spent so many thousands of dollars over the last few months, racked up so many hundred thousands of points. Why don't I keep it longer? Now, this person has access to my data as soon as I call them. Similarly, when I go and on my T-Mobile web app, I see a historical analysis of the bills I have paid, the monthly analysis of how much internet I have used. And this gets refreshed every few minutes. So the third part of the new workloads which are coming up includes continuous ingestion and continuous transformations. Now let's flip the lens from which we are looking at it. Let's look at it from a database point of view. What does a database see from, when these workloads arrive at the database? Here, I show you the query distribution by runtime for Redshift Fleet. On the x-axis is the bucket by runtime, 0 to 10 millisecond, 10 millisecond to 100 millisecond, and so on. On the y-axis is the percentage of queries which fall into each of these buckets. The green line shows the Redshift Fleet data, and blue line shows TPC-H, and the yellow line shows TPC-DS. As you would see, most of the queries fall below 1 minute. In fact, 99% of the queries which Redshift sees are less than 60 seconds. But there is a long tail of queries which stretches over hours and hours. Now, TPC-H and TPC-DS, and the 3 terabyte was the scale we used, captures only a part of this distribution. Arguably, if we used 100 gig or 100 terabyte, it could shift left or right. But then it could never cover the whole distribution. Now to dive deeper into this, let's split this workload into two: the long tail of long queries and dominant short queries. And the third part, which is not shown here, is the continuous ingestion and transformation. And let's see what kind of patterns do we see on Redshift Fleet for these. First, let's look at how much of the database capacity or resources are these queries using. This is the same chart. On the x-axis is the buckets by runtime. Y-axis is percentage of sum of execution time, meaning that we took the queries in that bucket, summed up the execution time in that bucket for those queries, and divided it by the total execution time of the queries. You see, if you look at the 10-second to 1 minute bucket, most of the queries, as I said earlier, 99% of the queries fall in those buckets. But they do not use the database capacity. Most of the database capacity or the hardware is used for long queries, the long tail. Interestingly enough, TPC-H and TPC-DS is able to capture that part, the long tail part here, but not so much the short. Now let's look at some of the plausible reasons why these long queries use so much of the database capacity. The first aspect we look at is query complexity. On an average, Redshift queries are not very complex. Like if you see here, on x-axis, there are operators, SQL operators, and on the y-axis is the number of operators. So average Redshift query has about 2 table scans, meaning either they are used as a join or a union or a subquery and so on. Only half the queries have joins and aggregations. But if we look at Redshift queries which are greater than 60 seconds, shown here by the dark green boxes, this number jumps up by 3x. The number of queries, the queries scanning on an average for these queries, the tables are 6 tables are scanned on an average. The joins increase by 3x. And if we look at TPC-H, which are shown here by blue boxes, and TPC-DS, which is shown here by the yellow boxes, we see they match closer to the Redshift queries which are greater than 60 seconds, and not so close to the average case. The next dimension we look at is data complexity, meaning that these long queries, they're complex. Second, we see that they may be scanning a more number of rows. This is shown by how the tables are distributed over bucket of rows. On the x-axis, we bucket the rows like 1 to 10 rows, 10 to 100 rows, and so on. On the y-axis is the percentage of tables which fall into each bucket. Again, we see the long tail effect here. About 70% of Redshift tables have less than 1 million rows. But there is a long tail of tables which have more than 1 billion rows. Now let's compare it to TPC-H and TPC-DS data. Now they cannot cover the full range of this distribution because the number of tables is just not enough. But what we see is for smaller, on the smaller side, the dimension tables. But the most interesting part is that the TPC-H and TPC-DS are able to cover the long tail of the number of rows present in this in Redshift tables. Let's look at one more aspect of data complexity, which is column skew. In general, the skew in Redshift tables is very high. We show it here. Like on the y-axis is a measure of skew. It is basically measuring how different the column value distribution is as compared to uniform distribution. So the higher the number, the higher the divergence. We see here the Redshift fleet data is shown here in blue line. And 50% of the columns already have 100x the skew than a uniform distribution. While for TPC-DS, the 100x is reached at 99th percentile. TPC-H does not have much skew because it mostly has a uniform distribution. And again, we see the long tail here. The 99th percentile of Redshift reaches very high numbers of all the way up to 10 to the power 14 or 15. So what did we learn? We learned that there is a long tail of queries. They use most of the database resources. And that's probably because these are complex queries running on large tables and run into data skews, which does not make them too scalable. So how should a database work with this kind of a mixed workload? It is obvious that the warehouse needed to run these long queries should be a big warehouse. But if we run the short dominant workload also on such a warehouse, the cost would become prohibitive. Therefore, today's database systems allow workloads to be split. The customer can create a big warehouse for their long queries and the smaller warehouse and a numerous of them to address the short dominant queries. But this needs orchestration on part of the customers. This isn't the best experience. There are ML-driven techniques today which can split the workload, create warehouses which are commensurate in size to these workloads. Now let's switch our focus to the other part of the workload, which is the short query workload. What are the attributes we see for these short query workloads? One of the most important ones we see are the query repetition. And that makes sense because these short query workload is coming from line of business users, from customers. They're not coming from analysts who would arrange tables in different ways or pick different columns. These are canned queries. So the query repetition we see is very high. On the y-axis, we plot the repetition percentage. And on the x-axis, the percentile of clusters. The first chart shows the query repetition. The 50th percentile of clusters has about 50% of the queries repeating on a per day basis, which is represented here by red and green line. On a weekly and monthly basis, this number goes up to 75%, which is represented here by the orange and the blue line. Now, if we take a step back and remove, let's say, filter values from the queries and consider only query templates, this repetition percentage then goes all the way up to 80%. Another attribute of these workloads is burstiness or spikiness. This chart shows a measure of spikiness on the y-axis. And percentile of clusters on the x-axis. So this measure is basically comparing number of queries run in the current period as compared to the last period. And higher the number, higher this difference. So for 50th percentile of the cluster, it's only about 10% different on a daily basis, which is the first chart. But if we consider on an hourly basis, this number jumps up to 40%. So these workloads are bursty. So what kind of features should a database have to address these workloads? First, to address the repetitiveness, the idea is to cache, and not compute. These database systems have features like result cache, which can cache data when the query comes in first, and if it comes again, it can return the same data. These systems also have materialized views. So if a query comes and a materialized view can be used to answer that query, the query gets rewritten automatically to use the materialized views. This reduces the compute, the cost, and improves the latency of such queries. Now to address the bursty nature of this workload, the idea is to auto-scale, create serverless architectures around these databases, so that when there is a burst of queries come in, these serverless instances can be spun up within a few seconds, and address the spikiness using one or more of warehouses, and then go back down when there is no workload left. Now let's look at the third part of the workload, which was continuous ingestion and transformations. From the database system, it looks like write queries. And for Redshift, we see this split evenly between read and writes. We see almost 50% of read queries and 40% write queries. 10% are system queries. And when we compare it to TPC-H and TPC-DS, TPC-H has almost 80% of the queries which are read queries, and 20% which are write queries. What this implies for a database is that the write scalability is as important as read scalability. Means that they have to create data warehouses which run in parallel, which split the workload, and are able to write on the same data set. With this, let's try to summarize. What do our customers want? They want database systems which can satisfy the traditional business analyst use cases, which is to crunch large amount of data for complex queries as fast as possible. Second, these database systems should be able to handle the canned queries coming from line of business users and customers. These are short queries, repetitive, and bursty in nature. And finally, these database systems should be able to handle a large amount of writes. Therefore, we need a database system which can handle long and heavy tail queries, short, repetitive, and bursty workloads, and as many writes as reads. And we need new benchmarks which can measure these databases and provide customers with feedback on which database to choose. Thank you.